Good morning, everyone. My name is Jaume Planas, and I'm going to give a presentation on my final master thesis, MobilitApp, using deep learning models to automatically identify transportation modes. I want to start this presentation by talking about the topic that gives sense to the MobilitApp project, which is urban mobility. When we think about urban mobility, we imagine something that probably started looking like this, that we wish that today would look more like this, and we dream that in the future will look like this. But in real life, when we think about our daily experience, we realize that for most of the times at least, it looks more like this. Because yes, traffic has become one of the fundamental problems that our society faces. And it's a problem because it affects us in three fundamental ways. It causes money, it causes time, and it's bad for the environment, which, as a result, is bad for our health and for the future generations. Since the problems of traffic are so relevant, great efforts have been made all over the world to try to find creative solutions to tackle these problems. Solutions as diverse as the creation of low emission zones, the introduction of congestion charges, or even giving away free public transport cards in order to incentivize its use. But so far, none of these solutions have managed to achieve complete success, and there's no city that has actually managed to solve all problems related to mobility. That's essentially because mobility is a very complex phenomenon and requires a lot of information in order to make precise decisions. Luckily, we live in a digital world and we have tools that can help us get all this necessary data in order to completely understand mobility. One thing that we all have with us is our smartphone. So what if we were able to aggregate data generated by all the smartphones of all the citizens and use this data to extract information about their mobility patterns? This information could in turn be used in order to by mobility planners in order to make more efficient allocation of resources and better decisions in general regarding mobility. That's the idea behind which MobilitApp was born. MobilitApp is a mobile application designed with three fundamental objectives: identify the transportation mode in real time, record origin and destination of the user, and extract an anonymous profile of said user. With these three fundamental informations, we have the data from which routes are being made at all times in the cities, from which position the users are going to each other, and which transports are being used, and we can use it to generate what's called the mobility matrix, that are representations of all the traffic flows within a city. Combining this with information about the age range and the gender of the users, we can have a very complete picture of all the different groups of people and their mobility preferences. So now that we know what does MobilitApp want to achieve, let's look at how it works. Here we can see the general architecture of MobilitApp. We have divided in the control plane, which is the application seen now by us, the developers, but in the future by mobility regulators or whoever is managing the application, and the application seen by the user. For the user, the application is completely transparent. It has a built-in model that is able to detect the transportation mode and send all the relevant information to a remote server. But for the managing authorities, this remote server is the door through which it can obtain data that can use for us as developers to basically to generate more new models that perform better, but also for managers of mobility to create these data sets of information about the patterns of mobility of users. Looking at concrete details of the implementation, let's start looking at how geolocation is managed. The application uses essentially the API of Google, more precisely the location manager functions that are built in Android applications. Regarding the obtention of data, we use data generated essentially by three sensors, built-in sensors of the smartphones, which are the accelerometer, the magnetometer, and the gyroscope. This data is collected in CSV files that we obtain through a campaign with volunteers, our family and friends, up to 100 volunteers generating data. And this data, with these volunteers, we managed to obtain almost 3,000 different CSV files with data. To these files, we applied different data processing techniques, such as the introduction of a sliding window, feature extraction, outliers elimination by Mahalanobis distance, and we obtained a final clean data set as follows. You can see here the number of samples for each particular transport mean. As you can see, the dataset is completely unbalanced. This is because, as I mentioned, we relied on friends and family and contacts for the generation of data, and of course the number of users of cars is much higher than the number of users of e-scooter, for example, and this is why we have a much larger amount of samples from cars. Finally, with this dataset, what we did was to train a machine learning model. More precisely, we trained a deep learning algorithm using the LSTM architecture, long short-time memory. Long short-time memory is a particular kind of recurrent neural network that is able to learn long-time dependencies in time series, like precisely the raw as data generated by the sensors of the mobile phone. So with this model, we decided to make different experiments. First of all was hyperparameter optimization, and then the training of the complete model. So let's look at the results. For the hyperparameter optimization, we tried up to 24 different combinations of the hyperparameters dropout rate, stacked LSTM layer numbers, and patch size. And we compared their performance based on their validation accuracy and validation loss rate. As you can see, the one that performed better was a number of stacked LSTM layers set at 256 per 512, a dropout rate of 0.1, and a batch size of 64. So with this optimal configuration, we trained the model once again, this time for 120 epochs, and we obtained an accuracy of up to 98.76% and an F1 score of 98.75. More importantly, if we look at the confusion matrix, we see that of the 11 different transport means considered, for 10 of them we obtained an accuracy that was above 90%, and the only one that fell short of this threshold was the e-scooter that registered an 84.6% accuracy, essentially due to the small amount of data that we had for this transport. So seeing that the performance was so good, we said, okay, now let's look at why it's performing so well, which sensor is playing the most important role, and even can we eliminate one of these sensors to make a lighter model. So remember, we had 3 different sensors, the accelerometer, the magnetometer, and the gyroscope. But for each of these sensors, we have 3 different axes. So in reality, we have up to 9 different features. To these features, we applied L1 regularization, and we obtained these results. As you can see, the features related to the magnetometer are the ones that actually have the most important role in the classification, whereas others, such as the y-axis of the accelerometer and the x and z axis of the gyroscope, have a much less important role. So we ask ourselves, okay, can we eliminate these less informative features? And we did so. And these were the results. As you can see, for most of the transport means, the performance remains very high. But there are 3 particular cases that have suffered a significant decrease: the bicycle, the e-scooter, and the motorbike. Now, if we think about the features that we have eliminated, which are essentially related to the gyroscope and the transport that are showing a poorer performance, we realize that actually bicycle, motorbike, e-scooter are precisely by their precise dynamic nature are the transports in which the changes in inclination are more frequent. And this is why eliminating features for the accelerometer actually decreases its performance so much. So this brings us the question, is this model a good alternative, or is it better to stick with the original one? And the answer is it depends. In our case, that we wanted to be able to classify the maximum number of transports and emphasize on micromobility solutions such as precisely the e-scooter or the bicycle, this approach was not the most interesting one because we are losing the capacity to classify 3 of these transports. But if, for example, the task was just intending to differentiate car from other transports, or car from bus, or metro from train, then in this case, this model could be an interesting alternative because the general metrics remain very high. There's just a decrease of around 1% in the accuracy, but the model is much lighter, both in terms of its size and execution time. But in our case, this is, as we mentioned, not the objective. And for this, we decided to keep the complete model with 9 features, integrate it in our application, and do some real-time tests to see how it performs on the field. For the first test, we just let the mobile phone rest in a flat surface, and we saw that the activity was correctly classified as stationary, of course. But more importantly, you see in the picture on the right the entry that was registered in the server, in which we can see that the capture was correctly labeled as one done by a man aged between 18 and 29, and containing information about the time when the capture started and ended, and the coordinates of the origin and destination, which of course in this case are the same because the activity was stationary, so there was no change in position. But moving forward, we said, okay, now let's walk and see how it does. And you can see that the activity was correctly classified once again as walk, with just a very small number of samples misclassified as run. But looking at the capture in the server, we see that the origin and destination coordinates are now no longer the same. And in this map, you can see the actual coordinates that were registered and how they almost exactly match the route that was made, because the destination was this metro station of Fira, so there's a very small margin of error. Once in the metro station, of course, we took the metro and we went from Fira to Zona Universitari. You can see here that the activity was once again correctly classified as metro, and the coordinates and hours were correctly registered on the server. Finally, we tried the application with the car, and the results were essentially the same. The activity was correctly classified as car, just a sample misclassified as bus, but all the coordinates and hours are correct with the small margin of error that we have already mentioned. So what does it all mean? Well, first of all, we see that MobilitApp is able to accurately predict transportation modes in real time. We have an accuracy of 90% for 10 different transport means, and we have seen that magnetometer is the sensor that actually plays the most important role, but that there are different models that can be trained selecting particular groups of features that can be interesting for particular contexts. We have also seen that MobilitApp is able to record the location where each capture is made and the user profile of the user, including its age range and gender, and that all this data is collected and anonymously sent to a server controlled by us. So with this, we believe that the application is essentially ready to do its general job, but there are still some fields of improvement that we believe are important to keep in consideration for future work. First of all, we have seen that the dataset is unbalanced. It could be interesting to solve this and especially obtain more data for these transport means that have performed less successfully precisely due to this low amount of data, such as the e-scooter is the most obvious example, but also to introduce other transports, such as, for example, the electrical bicycle. And another thing that should be considered is that a lot of trips done in cities are multimodal trips in which different transport means are being used. Now, to capture these trips now with the current version of the application, the user has to start and end each capture each time that it changes transportation mean. But it would be interesting to introduce a feature in the application that was able to identify changes of transport by itself, thus reducing the number of times that the user has to start the capture. With these two improvements, we believe that the application would be completely ready for its deployment, and we will be able to finally complete the development of MobilitApp and luckily integrate it in MobilitApp projects so that it can help make problems regarding mobility less of a problem and probably more of something that is improving and make MobilitApp in general a much more enjoyable experience than what it is nowadays. With this, we close this presentation. Thank you very much for your time today.